Okay, looks like we can start. Welcome back, folks. Well, it looks like another small class. Hopefully we'll get a couple others, but we have a representative that made it to class today. Appreciate it. And another one in Zoom as well. So, at least we have a person representative on both sides of the classroom. For today's class, we're going to be finishing off section 15.3 pretty shortly. We're on the last part of the last example. These are pretty long problems, so sometimes pacing these to end just right doesn't always work out like this time. And after we finish that section, we're going to move into section 15.4, the last topic of the entire course. So congratulations, everyone, for getting through it. Also, the last quiz number 11, this one's based heavily off section 15.3. So just doing one of those examples. Once you figure out which test it is, the left tail, right tail, or two-tail test, you can just use one of the examples out this section as a model of how to get through all the parts. So, well, after we are done with section 15.4, I'm hoping to have it done Monday of next week, potentially. We'll then be moving into just reviewing for the final exam. So the review will probably start sometime on Wednesday, maybe finishing off a last example on the start of Wednesday. And all of Thursday, we'll be reviewing for the final. We'll talk a little bit more about it, but so far there's standard materials, version 1, version 2, we saw for the other exams. And this is the real final exam that was given a year ago in my class. So this is another great resource. And I think that's pretty much it for the announcements. Any questions or comments at all, folks, to start us out today? Yeah, absolutely. So this is a great way to say it, just a capsule summary view of pretty much what we've been doing in section 15.3. So this part right here is the current section that we're about to finish off, handling the categorical data. And just for the sake of we're about to take a look into the formulas, I thought I'd put them on the Canvas page right now so we can see how they compare. The formulas are all in section 15.4, but for a quick view, the reminder is we're not doing anything too different. We're changing from a parameter P. In quantitative data, the parameter we're estimating this time through a test is mu. So that means the hypotheses look different. We have a null hypothesis that mu equals a hypothesized value mu naught. And the test statistic also looks different. It looks a little bit different than that. That's a mistake I made. Z is actually T. We go back to the student's T distribution. We have to compute degrees of freedom. But in place of p hat, we just put in y bar. And the denominator, instead of a standard deviation, we use the same old standard error that we did with confidence intervals. So we'll be delving into this formula below pretty shortly. Other questions at the moment? Okay, thanks for asking about that. Well, again, it's a short class, but if you're curious, we do have one representative also, or not short class, small class. We have another representative in Zoom as well. So glad you all made it today. Well, we left on the last parts of the last example, so let's take a look into those notes. It's section 15.3, and here's how it went. This was a kind of a funny study in a certain sense, and maybe slightly depressing as well, about the USA Bill of Rights and American adults' knowledge on it, being able to pick it out of a multiple choice test. We were looking for evidence that less than half of Americans can identify the correct definition of the Bill of Rights. So that's why we formed the left tail test we see down here. P is the population proportion of those people, and we're saying less than 50% of successes in the population. So when we maneuvered through these data, first thing we had to compute is p hat. That's just putting the context together, really. Then the test statistic was a matter of finding the distance between p hat, p naught, which was the value 0.5, divided by the standard deviation. So p naught went into that standard deviation, not p hat. We divided and got negative 2.5 standard deviations. Next tricky part is because it was a left tail test, right at the test statistic Z, we had to shade specifically to the left. Then it was just a matter of putting this information into the calculator for normal CDF. P-value came out at 0.0048, but that's a kind of success, a sad success because the story isn't nice, but it means the thing that we were looking to find evidence for, the alternative hypothesis, we found a lot of evidence. This is a pretty enormous amount. The p-value of 0.0048, let's write in a quick comment, is absolutely less than 0.05, which was the significance level alpha that was set for on this particular study. So that means we will reject H naught. So there it is rejected. And we have significant statistical evidence that HA is true. So that's what we're going to do on the next. Just write down that final conclusion. That was the last part. I didn't want to push class 5 minutes beyond penning in this last bit. But any questions at all, folks, with the rundown before we finalize this last example? Okay, let me put down just a border to say our answer is just going to be up here, and this is just for easy reference. When it comes to the practical conclusion, it's really just all about saying if you had the evidence or not and reading out whatever this is. So at that value, for the p-value less than alpha, we can now say this study provides significant statistical evidence at the 5% significance level that this statement, p less than 0.5, is true. We have to write it out. And I think we've mentioned this before. It's tedious to write this out twice, I know, but bear with me. If you write out once, it just makes you way more accurate when you get to the very end part, writing the overall conclusion. So let's go through this painful part, just writing this again. We have significant statistical evidence that the population percent or percentage of people who can correctly identify the definition of the Bill of Rights. So we had significant statistical evidence. I forgot the part among all Americans. Let's say that just to be specific. Among all Americans, just double checking here. We said people, they did say at one part, if we're being a little nitpicky, that this was specifically adult Americans, so not middle schoolers or high schoolers that might be learning about this. Let's put this in on our final statement here, just to be a little bit more specific. Among all adult Americans, is less than, you could just say half to match the question, but if we're going through here and reading this out a little bit more verbatim, I'll rewrite that as a percentage because we said percentage up here. We'll say is less than 50%. So that's finally our conclusion. Less than 50% of adults in the United States of America can correctly identify the definition of the Bill of Rights in a multiple choice test. Kind of an interesting study that they came up with. Says a lot about civic education in high school, middle school, maybe as well. But any last questions at all, folks? Getting to the final statement of this test here. Okay, well, we did it, folks. That's half of the hypothesis testing, the categorical data side. Next, we're going to turn it over into quantitative data. But really, once you've seen how this goes together once, changing the data type is really not the hard part about this. The hard part is seeing how to get your p-value out, putting together the test statistic, which gives you the p-value, knowing what decision to make to reject or fail to reject, and writing down your conclusions. Those are kind of the hard bits. But when you change it to quantitative data, you're just doing this all over again. It won't say population proportion or percentage, you'll say population mean. And so it starts to become pretty familiar, I think, to a lot of people in the very next section. So it's not as rough as this one where we're just starting out. Let's now change gears and take a look at the quantitative data side. Okay, let's maybe just as a way to kind of pause, mentally gather these results. This is the test that we just ran, where we have a test statistic z measuring the statistic p hat against the distance of the hypothesized value divided by standard deviation. Now with quantitative data, the parameter is mu, and the statistic is the sample mean, y bar. We subtract the hypothesized mean, mu naught, but we don't have a standard deviation any longer. This is one of the weird things that we talked about a little bit last class. Assuming the null hypothesis is true doesn't give you the standard deviation like it does with categorical data. That's because the formulas for the categorical data had just one parameter. Knowing what p is gave you both the mean and the standard deviation all at once. Here, it's still unknown, so we still use the standard error. That just means we were using the same formula that we would have used in a confidence interval. That's kind of nice in a way. So here's how the notes go. Like any section on statistical inference, it has the central limit theorem because this is what controls everything. All of our methods, whether it's a confidence interval or a hypothesis test, it comes right out of here, the central limit theorem. And this one's just the statement for means. If you let y bar be the mean of a sample of size n, where it came from a population with the true but unknown mean mu and true but unknown mean standard deviation, then the sampling distribution turns out to have a normal distribution shape. The mean is the mean of the population, the original one, mu. The standard deviation changes a little bit. Standard deviation is the standard deviation of the population divided by the square root of the sample size. And we have other interesting informations here. If the distribution of the population is normal, the y bar is also exactly normally distributed. But this is something rarely occurred exactly as true in practice. So this is the statement that we usually default to in the central limit theorem. If the sample size n is large enough, then the sampling distribution of y bar, a separate population that the statistic actually came from, can be approximated nicely by a normal curve. Even when the population is not normal, say severely skewed, you just need a large enough sample size n. And this is the extremely blunt rule of thumb we mentioned before. In practice, for many situations, but not all, in many situations, a sample size at 30 or higher essentially tells us this approximation is a good one. There's something else going on you might have noticed I skipped over. This is the same thing that happened with the condition checking in chapter or section 15.3, as well as in chapter 13, confidence intervals for proportions. If we have a finite population, then we might have a problem if more than 10% of the population is included in the sample. This whole thing actually starts to break down. And so that's why you saw when we did condition checking a little bit more carefully with categorical data, that was a condition that our sample can't exceed 10% of the population size. We're not going to check the conditions super carefully in this section, but I felt like this is good to leave in here just as a reminder for the sake of completeness. So that's the central limit theorem, the major statements it gives us, a condition and when it's usually true as a rule of thumb. But like we were mentioning before, using the central limit theorem is tough because we're doing a test on mu. That means we know mu is unknown. We can't just assume a value for sigma. If mu is unknown, so should sigma be as well. And so that's why we go back to the standard error. And we're also in the t distribution, so we need degrees of freedom. Example one is kind of like a warm-up problem, just revisiting these two different definitions. Well, let's work through example one. First, any questions at all, folks, with any of the statements here? Okay, so we've seen example one before. I think we did entire confidence interval on this. So it's some familiar data. It says the Federal Bureau of Investigation compiles data on robbery and property crimes, publishes information in population at risk and selected crime indicators. So that article there, there's a simple random sample of 25 pickpocket offenses in this data set. So that's our sample size. We're also given a sample mean loss of $513.32. So we can call that, say, y bar is 513.32. And we have a sample standard deviation loss of $262.23. So that's going to be the value for S, 262.23. So those are all the values we have so far from the data. Y bar estimates the unknown mu, and S also is an estimate. It's an estimate for the other unknown, sigma, the population standard deviation. But because we don't know the true standard deviation of the population, that's why we use the standard error for confidence intervals and for quantitative data. We're forced to use it again in hypothesis testing. So when you see this, SE, it stands for the standard error. But there's two kinds of standard errors. There's one for p hat and there's one for y bar. Standard error of y bar goes through this formula. It's S divided by square root of the sample size, n. So we use it for confidence intervals, but it's been a while. Hypothesis testing has a way of kind of scrambling your brain a little bit. So think of this as, again, just kind of a review problem. We put in the value for S, 262.23, divide by square root of sample size 25. So we get a value out, 262.23. Square root of 25 is 5, so you can save some steps on the calculator by just going division by 5. And that tells us the standard error, which is an approximation of sigma over root n, is 52.446. It has units, that's in dollars. So if you want to squeeze in that unit, that would be kind of nice as a reminder, but not required. So we've got it, folks. That's our standard error. And just a couple reminders. The standard error is approximately the exact but unknown standard deviation, sigma over root n. So that's what the standard error provides for us. And maybe another reminder, since we're getting close to reviewing for the final exam as well, there's two standard errors in this class, confusingly. Standard error for y bar looks like this, but just a quick reminder, if the data was categorical and we're doing a confidence interval, that's when this standard error comes into play. It's through the formula square root p hat, 1 minus p hat, divide by n. Not the same thing you use for hypothesis testing, confusingly. So we've got a standard error. I like quantitative data because you use the same exact formula, whether it's a hypothesis test or a confidence interval analysis. It's always that object there. Any questions at all with standard error? Okay, next thing we needed when we did confidence intervals in chapter 14 was degrees of freedom, and we need that here as well. for degrees of freedom, we use DF as just a shorthand. The formula is just n minus 1, so it's a fantastic formula. We just have to remember to subtract by 1. So it's 25 minus 1 to give us a value 24. Now, we needed that degree of freedom whenever we're doing a confidence interval, and we had to use inverse t. But it's different this time. We don't use inverse t. We're going to be using this one. Let's take a preview of the calculator operation. So notice you used normal CDF to get a p-value for categorical data. But if the data is quantitative, you use all the way down at the bottom, T CDF. T for the T distribution, normal for the normal distribution, and CDF just stands for cumulative distribution function, just a fancy way to say gather the area.
That's new, right?
That one's going to be new, absolutely. But you know it's going to look familiar because when you hit enter on that, there'll be a lower value, an upper value, and you just feed into it the degrees of freedom. So that's the part that carries over from the last chapter. You're going to calculate a new test statistic, but where it goes, where the upper and lower values are, exactly the same as in the last section notes. So just as a reminder, let's leave this as a screenshot. We need degrees of freedom for this part right here. We go to TCDF, and that's where we'll use the degrees of freedom. So this operation right here is to obtain the p-value.
Is that gonna be on the C, like we scroll down on your notes? On the example?
Actually, I don't think I have a part C to these,
Oh,
to the example one if you're referring to. Gotcha. Well, this is kind of just the review topics on how to do all this stuff so far. The review was the degrees of freedom, the standard error, but this is the new part where we're going to get our p-value from TCDF. So we'll do this only when the data is quantitative. Normal CDF p-values come out only if we're dealing with categorical data. Well, let's take a look into the next formulas. Any other questions at the moment? No, not right now. We would have to have a test statistic in order to really use it. So for as far as part B went, getting the degrees of freedom was really the end of part B. And I'm not sure where I ended up there. Let me get out of there on the calculator. Okay, well, we're about to use these formulas, so that's the good news. We're about to calculate a standard error, get the degrees of freedom, and do a test statistic and a p-value. But first, here's the whole method. We call this the one sample t-test for a population mean mu. There's other tests. If we have two samples we're dealing with, it could be the two sample t-test, but we have limited time, so this is a nice last topic for introductory course. We use this test if we have the following two conditions met, kind of parallelism, good parallelism from the last time. The sample has to be a simple random sample from a population of interest. That's what we hope for in our hopes of hopes. And if it's not a random sample or not even a simple random sample, if the sample we know is selected in a way that is representative of the population, we should be concerned by being told it's just representative. But that allows us to pass this condition and say we at least have a representative sample. We possibly can give a good conclusion for the population. Second condition is, well, there's a lot to this condition checking. If we had the time, we would output a histogram for all of our raw data, see how skewed that histogram is, and judge if the sample size is large enough for the central limit theorem to really work. But because we're on limited time, this is the major condition we would look at. The sample size is just large enough, bigger than or equal to 30, tells us that our population should be approximately normal, and this condition should pass. This is not to say that a sample size low, like sample size 5 or 10, can't be used. But what it is saying is, if you have a sample size of 5 or 10 on the very low end, your data should look pretty symmetric, because if there's any hint of skew or outliers on a really low sample size, we cannot use the fact that it's going to be distributed normally. The sample size would be too low. But beyond the condition checking, here's the test statistic we were mentioning at the top of the notes. Very similar to what we just calculated. In place of p hat, we just have a y bar, a mu naught because the mean is mu itself, and mu naught is just the hypothesized value from before. Standard error is just going to be s over root n like we just calculated. We'll also need the degrees of freedom because we're going to be using, like we mentioned, TCDF. In our calculator. So degrees of freedom is part of what we would put in there. Beyond that, there's 3 tests: the right tail test, the left tail test, and the two tail test. And I left this blank as well, but this is kind of just a review, really. When it's a right tail test, it means here we shade to the right.
Get that other condition.
Down here. Gotcha. So for the gray then here, we'll shade to the right. For the left tail test, we'd shade to the left. But for the two tail test, that's where it gets kind of complicated. So we'll draw out 2 diagrams for that. But really, it's just a big refresher on what we did for the hypothesis testing in the last section. Other questions at the moment? Okay, well, let's draw our quick diagrams. When it comes to doing this kind of stuff, sometimes you can know exactly what goes into the calculator just by a simple sketch. Well, we mentioned before as well, if this was a final exam question you're about to do a p-value for, the sketch is worth partial credit. So if anything goes wrong in the calculator, you could get a significant amount of partial credit just from analyzing this diagram. But this is not the normal curve, it just looks like one. This is the TDF distribution, still centered at 0, and your test statistic t, whatever it comes out as, let's say for a left tail test, oftentimes t would be negative, although that's not required. It could be out here, and this area would be the p-value in this situation. Then same logic as before. Or hang on, shade to the right. This is supposed to be a right tail test. Somehow I got that flipped in my mind. Let me try again on this. Yeah, right at the very end there. Let's see if we could just control Z that out of there. Okay, so let's put T here, shade to the right, oftentimes in a right tail test, but not always. We expect this to be a positive value. It could be negative, but that would be an unusual situation. So shade to the right to match the right tail test. That looks a little bit better. Then in the TCDF function, let's take a look at it again. Let's go second bars, TCDF, so option 6. It just wants a lower and upper, and whatever you said your degrees of freedom were. So in a right tail test, the test statistic T is input 1, lower. Because we're shading to the right, input 2, upper, is 10 power 99 in that specific test. So that's what would go in those locations. Again, this should feel kind of like deja vu. We've sort of done this before, except, oops, didn't mean to throw the pen, except we called this the N01 distribution, and we called that Z instead of T. Well, other questions so far before we go to the next? Okay, so on this one down here, it's pointing to the left, so that means this one's a left tail test, and this is the one where we would in fact shade to the left. So here's another quick diagram. This is the TDF distribution centered at 0, and T could be very far to the left. This looks like statistical significance in this version right here. Whereas the one above, that looks like a good amount of area. So this would be non-statistical significance. So shading to the left would look about like this. And now we just changed the order of what's lower and what's upper. This time the lower value, we're going to the left forever in the shading. So input 1 lower is equal to negative 10 power 99. Input 2 upper is the test statistic t itself. So left tail test and right tail test go together in that way. But the two tail test is more complicated. This one's harder to say. It's either you double the area to the right of the test statistic t when t is positive, or to the left. Yeah, go ahead. Yeah, absolutely. So the buzzword somewhere in the problem is going to say, look for evidence of something higher or something greater than. It may not say greater than exactly, but something is going to say that direction. Absolutely. Same for the less than. You're looking for evidence that something is smaller. So they might say literally less than. And for the not equals, this one's pretty tricky. You're looking for, say, something that says is different from. So just a quick review on what those might look like, because that's kind of half the battle, decide what the test is so that we can get the right p-value in the shading. Let's do a quick review of some of these that we came across. So example 1 was kind of a warm-up example, but then right down here, example 2 is where it started. Example 2 is saying, do the data provide sufficient evidence to conclude the percentage who currently use marijuana has changed? That doesn't mean go up or down. So that one wasn't a right-tailed, it wasn't a left-tailed. Looking for change in either direction was the two-tailed test. Then down on here, let's see, example 3 somewhere. There it is, finally, example 3. The question was, does the data provide convincing evidence that more than a quarter of Americans have sent a text while driving? But once they said more than, that was the greater direction right here. So more than would be conflated with greater than on this one. And for the last one, this is a good time to spend on this because, again, getting these last details just right is not always easy. There's so many little pieces that go on with hypothesis testing. But right here, where they told us to determine if there's convincing evidence that less than, they used a literal less than in this problem, which is kind of nice. That's why it was a left tail test. And that's why when we shaded, we were shading to the left right here. So somehow, some way, the problem has to indicate what direction the test should be. And that's how it will be written as well as a quiz problem, as well as a final exam problem. There'll be a buzzword somewhere that says one or the other. If you're not sure which it is, if you just can't tell what the direction might be, this is the one to fall back to. It's the default one. And if you did this test when it should have been a less than, I would still say that's a lot of credit. I would give you almost all the credit on the problem if everything else is right. Say the 12-point problem, if you ran it as a two-tailed test when it should have been a left-tailed test, I would give you 11 points out of 12 because that's such a strong, important concept that this is a default test that knowing how to run this one is very, very important. Which is annoying because there's two different ways to get the p-value depending on your test statistic. So it's complicated to describe the p-value to this one. So let's split this up into two. But other questions or comments so far? Okay, the way we get the p-value is, it's literal when it says two-tailed. If you find the one tail area, you actually double it to get both of the tails, both of the areas in the tails. But doing this mechanically, it really looks like this. Figure out where t is. If t is positive, your diagram is going to look like this. TDF distribution. Let's put T here. We're shading to the right, but because it's a two-tailed test, there's also shading to the left at the same exact time. We need both of these areas. But as long as you do multiply by 2, find the p-value for this one and just double it, you'll get the right area each and every time. So this one, if we run this and get that t is positive, we would use the test statistic t for the lower. And then for upper, it'll be 10 power 99. But then don't forget, critically, double it. Let's highlight this, double that area so you can get both areas in the so-called two-tailed test. So that's if you get a positive test statistic. If your test statistic came out negative, it's the same sort of picture, but you're using just a different value for t. You're on the left end, and you're going to double that area instead. So here's TDF once again, 0 in the middle. Let's suppose your test statistic ends up here, so here's t. You would shade to the left of that value, but go the same distance to the right of 0, symmetrically to this end. You also want that area at the same exact time. So we have to do twice the area to the left of t so that we get the entire area for the two-tailed test. So if it comes out like this, we're doing a two-tailed test for hypothesis testing. I think this actually happens in the quiz. It's just categorical data, by the way. This would mean input 1, lower, is negative 10 power 99. Since we're shading to the left, going forever, input 2, upper, is the test statistic t on this one. And then we double that area. So this is what the graph will look like if we get a negative test statistic in the two-tailed test. So 4 potential situations really with 3 tests. Yeah, literal multiply by 2. And when we did that in the last section, here's what it looked like. Yeah, exactly. Just as you said. Let's take a visual of that because this is pretty confusing in my opinion. So down below, when we did a two-tailed test on these notes, 15.3, that was example 2. This one came out as two-tailed. Our test statistic, even though it's Z, it's the same logic in the diagrams below. This one came out as a positive. So we graphed it right here as a positive value. That was the lower, that was the upper. Just like on this one, I have these flipped around. Then once we got normal CDF using lower and upper, it gave us a value, but we have to double it. So that's where we did the ×2 in the calculator immediately after. And that's the p-value we actually used. So you'll hit enter on TCDF, putting in the information, but then go ×2 in the calculator right after. Does that make sense so far with using this method? Awesome. And I think that deserves special emphasis. Let's see if we can put this in here. After using TCDF and getting a value, this is only for the two-tailed test, hit ×2 in the calculator. So that's how we're going to do the doubling both here and here. Well, we got it, folks. That's the description of all the formulas. The diagrams look the same, but it's kind of just, again, a refresher on this kind of information. What's also the same, thankfully, is the decision we make. Just because we change the data from categorical to quantitative doesn't do anything to this table. So this is a literal copy paste with my only changes, the parameters are mu, the hypothesized value is mu naught. We still reject the null hypothesis when the p-value is small, smaller than the significance level alpha, and we make the conclusion we have found significant statistical evidence that the alternative hypothesis, HA, is true. It's all about that alternative hypothesis. If we have a large p-value, that will tell us that our data isn't so surprising or unusual. That's when we fail to reject the null hypothesis, and then we say, well, almost the same thing, except we say the study failed to find significant statistical evidence that the alternative hypothesis, HA, is true. So either way we look at it, we go back to the alternative hypothesis both times. We are effectively saying we either have enough evidence that this is true, or we failed to find the evidence that this is true. But never at any point do we make a conclusion we found evidence that the null is true. We never know if mu is equal to mu naught whatsoever. We're just trying to find evidence against that statement, just like in a court of law, the example we often come back to. So with all that said and done, I think we're ready for an example. Example 2 will definitely finish today, and it looks like we should be able to finish the third example for sure when we come back on Monday's class. So that will get us set up for starting our final exam review on Wednesday. So let's take a look at the information, see how this all comes back together. This looks like some pretty serious medical data. The ankle brachial index, ABI. Usually seems important when they give you an acronym, so let's highlight that. The ABI compares the blood pressure of a patient's arm to the blood pressure of a patient's leg. That seems like some important benchmark because you can imagine your blood pressure on your arm could be very different from where it is on your leg if you're standing, sitting, laying down. We're told next, ABI can be an indicator of different diseases, including arterial diseases, which can be all sorts of level of seriousness. And just for an interesting benchmark, we're told a healthy ABI is 0.09 or greater. We'll have to come back to that information there. So that's the setup so far. Now we're looking into a specific study now that we have the context. It says, in a study by M. McDermott and al., titled Sex Differences in Peripheral Arterial Disease, and a bunch of other things, in the Geriatric Society journal, the researchers obtained the ABI from a random sample of 187 women who have peripheral arterial disease. That kind of told us a couple things. The sample size is 187. It also told us what the population is. Looks like the population would be all women with peripheral arterial disease. So this looks really important as well. It seems to be indicating a population. Let's go with yellow on this. It tells us next, the results were a mean ABI of 0.64 with a standard deviation of 0.15. So now we have statistics from that statement. And I want to hesitate maybe from using blue for the mean, because I think this is a good carryover. We've been using blue for the hypothesized value. So I'm going to keep that color for that value. For the mean ABI here, I'm just going to call it Y bar is 0.64. But we can use this color for the standard deviation. Standard deviation, green is still on the menu for us, is 0.15. That's going to be S, because the standard deviation of the sample is 0.15, and this is for an index, ABI. And the 0.64 was the mean ABI. Units aren't required, but it helps with the context if we write them in. When it comes to quantitative data, our statistics maintain the units of the data. Okay, so finally with all that down, here's where a question mark comes into play. We mentioned before, if you see a question mark, sometimes that's a humongous giveaway That's probably the alternative hypothesis. Let's highlight this one as well. So this looks like it's almost certainly the statement of HA, just in ordinary words. It asks at the 1% significance level, so from here, alpha is 0.01 that we're going to use in the hypothesis test. Do the data provide significant statistical evidence to conclude that, on average, women with peripheral arterial disease have an unhealthy ABI? That's a tricky statement because when they said an unhealthy ABI, that's the form of the test. It's either a left-tailed test or a right-tailed test. This one's not two-tailed. Two-tailed would mean, is there evidence that they have either a healthy ABI or an unhealthy ABI? But this one's asking for a specific direction, yet it's not easy to kind of see what the direction is on this one. This is tricky. We have to use the context. A healthy ABI is 0.09 or greater. So when they say an unhealthy ABI, they're saying less than 0.09. That means this is a less than statement. It's a left-tailed test. So unhealthy is less than 0.09 because healthy is at 0.09 or greater, and we said unhealthy. That gave a direction. But because less than came up in a roundabout way, that means there's a less than sign here for a left-tailed test. That's pretty tricky context, but it's serious real world looking data. So it's not too surprising that it's kind of stated in a roundabout way. Any questions at the moment, folks, putting all this together so far? Okay, we're still missing one big thing when we read through all of this. What is the null hypothesis? What is the alternative hypothesis? The major thing we're looking into is, what is mu naught actually? Has anyone spotted the value to be tested, the hypothesized value? Not quite, yeah, that was the sample mean. There's another number here that we used to kind of determine if it was a left tail test. And that number, I wrote incorrectly, hang on. Less than 0.9, sorry about that. I was looking to this part right here. Less healthy ABI is 0.9 or greater, so I should have said less than 0.9.
That's it.
But that's the hypothesized value. That's the value that was mentioned in the alternative hypothesis. It was mentioned here directly. In fact, that doesn't always happen when we write out these tests. It's the same value here. So the null hypothesis is a statement of nothing's going on. There's no concern. The status quo is being maintained. What would that look like in this context? Having peripheral arterial disease means nothing's going on with your ABI. The hypothesized value is, it's right at that benchmark, 0.9, which cuts off healthy and unhealthy. So the hypothesized value is 0.9 in this problem. That's pretty tricky to spot. This example is, again, probably not a good one for a test question, but it would be fair game as a quiz if we had time for a 12th quiz. We ran out of time. And it's the kind of stuff you might see in the homework as well, where the context does take a couple rereadings to think about what's going on, what's really being asked on this question here. But once we pull it all together, essentially everything we did in the last section just sort of takes over. Let's mention one big thing though, just as a reminder, because notice you're using units, the fact that you have a standard deviation and a mean, the data is quantitative. What does that mean? The parameter is not P. There's no proportion of successes whatsoever. There's no success failure notion here. The parameter is mu. And that's why we're using mu naught for the hypothesized value, not a p naught this time. So when we go to describe the unknown parameter, the unknown parameter is mu. Mu is going to be the population. We cannot say proportion at all anymore. The right thing we have to say this time is population mean, or you could say average. Use the population mean. Then we have to say mean of what? What quantity? Is it points? Is it miles? Is it seconds? Well, we just look at the data. Y bar estimates that parameter mu. It's the average ABI at 0.64 for the 187 women in the sample. That means mu, our parameter, is the population mean ABI. But that's not good enough. This is just the data. We also have to mention the population as well. Whenever you wrote out those parameters, no matter what data type it is, the population is part of the description. This isn't the mean ABI for all people. It's not even the mean ABI of all women. We did say it's a random sample of 187 women, but the full context would be for all women with peripheral arterial disease. That's our actual population. So we'll say the population mean ABI for all women with peripheral arterial disease. So that's a tricky parameter, but they're all pretty tricky. That's why we've been spending a lot of time, usually on the part A steps, a lot of time talking about population versus sample to try to get a read on what this is. We have to mention somewhere that it's the mean. To hit the context, we also have to mention what is the value, the quantity we're dealing with. So there's got to be a unit. It could be mean points. It could be mean amount of seconds. Here's the mean ABI, ankle brachial index. And we also have to mention the population. So that's women with peripheral arterial disease. And that was a good call because it kind of emphasizes you're talking the population. So once we have that down, we go back to these kinds of hypotheses. Only change is that's a two-tail test, and we're doing specifically a left-tail test. We have the hypothesized value, and so we can now say test H naught, that mu equals something. Let's do like we did before and think about this. We'll fill in the blanks, give a little bit of space and say against HA, mu and then something, and then a little bit of space and say at. We're mentioning the level of evidence we want before we declare statistical significance. And it's a pretty high benchmark for evidence. But you know, that's probably good. This is a medical study. We wouldn't want to have this at 0.10 or maybe not even 0.05. We're saying we have to exceed a 1%, very small level of significance before we declare something is actually going on in this population. So next thing we fill in, on both of these hypotheses, we plug in U naught. It goes here, 0.9. It goes here, 0.9 again. The last thing we do decide on is what is the test. We're testing for an unhealthy ABI, which is less than 0.9. So because there's a literal less than, this is the left tail test. So we use the less than direction there. That means for the p-value, we'll be shading to the left after we get our test statistic. Okay, so part A takes about as much time to do as the real part A, which is just breaking down the problem, coming up with everything you could learn about through the context. Any questions or comments at all, folks, breaking up this context and getting through part A? And I noticed I did this in a weird way. I must have been thinking of the last section. Part A was the unknown parameter, and I have a part B of state the hypotheses. That was two parts at once. I guess I broke this up a little differently in 15.4. versus 15.3. Sorry for that weird distraction there. Well, we got through parts A and B and we didn't even know it, so we're off to part C. And this is where it becomes more of a math problem. So degrees of freedom, just cite the formula. When you see that in ordinary words, think df equals n minus 1. df is the symbol, the formula is n minus 1. Go back up to the sample size n, 187. Subtract by 1, and we have 186 degrees of freedom. So that's definitely not too bad. That's kind of weird quantitative data. Sometimes the formulas look a little bit nicer, which is strange. Next up is standard error. We usually highlight this in green in the last section notes, so let's keep the color coding for parallelism. It's a different standard error though. It's the standard error of y bar. Standard error of y bar has a nice formula. This is S divide by square root of the sample size n. So let's just plug in that information there. S was cited in the problem, highlighted in green. The standard deviation for ABI for this sample was 0.15. This is over the square root of the sample size n. And this is a common mistake I've made a lot. Once I wrote 186, it feels like that's n. So make sure you go up to 187, the actual sample size. That's always a weird and funny mistake to make, but MyLab Statistics has ways of really detecting when you make that mistake. So watch out for that one. It's easy to do. We'll round this to 4 decimal places. So just shove this into the calculator. 0.15. Divide by, hit second. That wasn't second. Let me try again. 0.15. Divide by, hit second and the power 2 button. That looks a little bit better. Divide by 187. And this is the standard deviation. If the computations are broken up and they ask you to round to 4 places as a separate part, in MyLab Statistics, they would know you used a rounded value. So we probably wouldn't get in trouble using 4 decimal places as opposed to like 5 or 6 that we used in the last section. So the approximation to the standard deviation is 0.0196. That rounds with carry. That seems to happen a lot. Rounding with carry, we get 0.0110. Does that look all right to folks on that last bit there? Okay, now that we've got the standard error, next up is the test statistic. This time it's called a t-test statistic. It's a good reminder that we're using the student t-distribution. The format for this test statistic goes t equals, before it was a p-hat, but that's categorical data. We use y bar, the mean of the sample for quantitative data. We subtract the hypothesized value, now a mu naught. And this part's actually really different. We don't divide by a standard deviation. We don't know it. We divide by the standard error of y bar, the value we calculated right above. So this is what the test statistic will look like in this section. Cite the y bar value from up top, it's 0.64. Subtract, go back to your null hypothesis. Mu naught is 0.9. And then just divide by, this time the standard error, 0.0110. And that gets our test statistic. It's a good reminder that all we're calculating here is just because we call it t doesn't mean it's different from standardized values. This is a standardized value that's going to calculate the number of standard deviations that our sample mean is away from our hypothesized mean of 0.9. In terms of approximate standard deviations, we're using standard error this time. So back to the calculator, let's go 0.64 minus 0.9. and divided by 0.0110. And look at that number. That's gigantic. That is negative 23 standard deviations. It almost doesn't matter what I round to, unless it's a MyLab problem, then they're going to be really specific about this. This is negative 23.6364. This tells us once we got that sample mean of 0.64 and compared against the null hypothesis is outlandishly false. The reason this is so big is because it's false, but also our sample is pretty large as well. 187 for quantitative data is a pretty large sample size. We can detect even small differences. So 23 standard deviations tells us that it looks like for this population, women with peripheral arterial disease, on average, almost guaranteed, they're in the unhealthy range. We are almost certainly rejecting the null hypothesis. It's a foregone conclusion. Yet, let's still do this step for the sake of what if it was negative 2.63, when it's less obvious. But this is going to give us a really, really tiny p-value. This connects back what we were talking about in 15.3, when sometimes your calculator is going to give you scientific notation. That happens in the homework in section 15.3. And it's going to happen here with such a large standard deviation, or a large test statistic rather. So when we go to calculate the p-value, we do have to make some reminders. That direction right there told us, right where the red dot is, it's a left-tailed test. So if we go to write out a quick t-distribution, like we did in the statement of all those formulas, this will be the T186 distribution, 0 in the middle. And I really don't have an accurate way to actually plot the test statistic T. I'll just draw it like this. It's in fact just off the page. It's out of the room, basically. It's so far to the left. So shade to the left, this is just to convey the information. This is not necessarily to scale any longer. Input 1, because it's a left-tailed test. Lower is negative 10 to the power of 99. And input 2, upper, is the test statistic T, which came out as negative 23.6364. Next reminder is we're using T CDF. So we're about there, folks. Let's grab that p-value. Hit second vars. It's option 6 all the way down here near the bottom, T CDF. So your calculator should have negative 10 power 99. This is the calculator's way of saying it. So if you have an E there, you could just leave it in that spot, and that works. But if you want to make it look exactly the same, here's what it looks like. Negative 10 power 99. Upper value is the test statistic T, negative 23.6364. We also fill in degrees of freedom, 186 came from part 6. Hit enter on all that. It's a left-tailed test, so we don't double anything, but wouldn't have mattered. We got a 0 on this one. Not because we made a mistake, it's because this test statistic is so far to the left that the calculator can't use something like 10 power 99 anymore to describe how small that area is. It might be something like negative 10 to the power of 203, some just extreme order of magnitude. Our calculators cap out at power 99 for orders of magnitude. So what we placed down here is, if we're going to literally round to 4 decimal places, p-value equals 0.0000. There it is to 4 decimal places rounded. So that's what happens whenever you get that as an output. It could have had something like e power negative 37, like we discussed in the last section. It'll be the same outcome. P-value is 0.000. But whatever the p-value is, for any reasonable alpha level, ours was at 0.01, we can say that this is less than 0.01, which is equal to alpha. So the decision we make is to reject H naught. We reject H naught, the null hypothesis, at small p-values, and it doesn't really get any smaller than that from what the calculator can give to us. All we now need is a quick conclusion, but that's not too different from what we've been doing all along. We just go back to what was the parameter, what was our hypotheses, and make a quick statement based off rejecting the null. So here's the null hypothesis rejected. We have evidence in favor of that alternative. So for the practical conclusion, we will say this study provides. Here it's good to put in kind of a nice word to convey that was a lot of standard deviations for our test statistic. Our p-value is essentially null. So we'll say this study provides overwhelmingly significant statistical evidence at the 1% significance level that the population mean ABI, we're reading out mu in this part right here of the alternative hypothesis, the population mean ABI for all women with peripheral arterial disease. We have a direction is less than 0.9. We already mentioned the unit ABI once in this conclusion, so we don't necessarily have to say it again. And a quick border here to say that's where the practical conclusion ends. And this screenshot here is just for a quick reference on how we got there. So it's really the same as before. We just say once again, what is mu compared against, I want to put in a specific coloring, the hypothesized value. We say we have found evidence that that alternative is true. All we're really doing is saying we found the evidence, that's this first line, and we write out once again what mu is to put it in context. Well, it should feel similar to what we did before, just slightly different things you're doing in the calculator, slight change to the formulas, but the main work of finding the parameter, writing down the hypotheses, making a decision on a p-value and a conclusion, all of that is basically the same exact kind of stuff. Big difference is we said mean instead of proportion in our conclusion. Well, any last questions at all, folks? Finalizing this very first one here. Yeah. Yeah, exactly. If it was a positive number, but it was also a right tail test, then it would also be essentially 0 as well. But if it was a positive number and it's still just a left tail test, here's what it would come out as. It would turn into a large p-value. So we'll go to TCDF. Let's suppose this was something like 12. So a really large positive value. Or hang on, that'd still be -10 power 99. The upper value, let's say this changed to a +12, but still a left tail test, and that's definitely possible. We would get something like this, a 1 instead of a 0. We would say 1 is greater than or equal to the 0.01. And so we would say we fail to find evidence that the mean is less than 0.9 in that case. So yeah, the fact that it was a left tail test and it was so large negative is what made this very, very, very small. Is that the question you're asking about? Gotcha. And just to turn it all around, if that was a right tail test, and we got something like this, second vars, TCDF. If it got a test statistic like say 3.5, it's a right tail test, so 10 power 99, it would have came out like this. Still really small. E negative 4 just means you move that decimal spot 4 places to the left. So this would have been 0.0003 after rounding to that amount. Still, we would say reject the null hypothesis in that case as well. Well, other questions at the moment, folks, before we call it a night? Okay, well, when we come back after the weekend, we'll review what we just did on these notes, move forward into the next question down below, and see how this one goes. This one's a little bit trickier because it doesn't give us the statistics. We have to find them from scratch, but really it's going to be more of the same. After we finish off that one, we'll be reviewing for the final exam. But have a great weekend, folks. We're nearly there. It's been a tough schedule, but I appreciate you all making it in. And even if you make it into watching the video later, you were here in spirit, so that's good enough for me. Have a great one. I'll see you all next week. You bet.
What section was it that we seen that formula with the standard deviation over the square root of the sample size?
That first came out chapter 14.
Oh, okay.
So that was the confidence interval look into quantitative data. So and chapter 14 starts out kind of rough at first, but once you get past where it says student t distribution, here's where it comes in, the statement of the confidence interval formula.
Yeah, when we used the E star.
Yeah, exactly. And getting that t star, we had to use inverse t instead of t CDF.
Yeah, before. And that's where you do the 1 minus the confidence level divided by 2, right?
Exactly, yeah. Yeah, I think confidence intervals are a little bit more trickier for that reason. Getting that T star out, that was a lot of additional work. I mean, I guess that's the same thing as getting the p value, just inverse t as opposed to t CDF.
We're gonna have 2 days of review before the final, or one?
We're gonna have two. Looks like we're on track to finish the last example in 15.4, our last section on Monday. So we're gonna spend all of Wednesday and Thursday reviewing. We might even just begin it on Monday after we finish that last example. Yeah. This one down below here. Awesome. Yeah, absolutely. Yeah, if you send it to me, hard copy, or email it to me, either way, I'll be happy to grade it for you. That's a great way to study, absolutely. Awesome. Yeah, that'd be a great way to do it. You bet.
Thanks for all your help.
Yeah, you bet.
Hey, you still have my quiz here?
I do, yeah, the one you turned in office hours?
Yeah, when I pulled out my calculator, I seen I had hit a button. Good, we're good.
Awesome.
I just wanted to make sure I wrote it on the right one. I hit that extra button again. That's ripped out.
Yeah, you could kind of almost remember the number being slightly different on here.
Yeah. feel like I'm in a pretty good spot, even if I didn't ace the final, I probably should still be able to get out of here with an A, I think.
Yeah, you're in a tremendously good spot. Yeah, you've been working hard all semester, so I don't think this filing is gonna be that hard for you, to be honest.
Right on.
If you're getting through these quizzes like you've been getting through and MyLab statistics, which is harder, then the final exam is just gonna be kind of, like a formality. Though you'll might see stuff there, couple things are a little tricky, but it's not gonna really hurt you.
Yeah. Well, thanks for all your help, man.
You bet. Thanks for your hard work.
Yeah. I put that in my, I don't know if you guys will get if you guys ever get the reviews that they sent us out, but.
Yeah, they send it to us after all the final exams and final grades are put in. They send it to us as anonymous data.
Oh, right on,
Yeah, they don't send it to us before because then that could bias our work somehow.
right?
You can imagine.
Everybody failed.
Yeah, someone gets
Everybody
pissed
got
off. Yeah,
Have a good weekend.
you too.